Wonderful. Welcome, everyone. I'd like to welcome you to our speaker series and welcome to my guest, Sukesh Aghara from UMass Lowell, and everyone joining today at MassCEC and beyond. This is our fifth edition of this speaker series where we're highlighting experts, pioneers, and practitioners from a variety of existing and emerging climate tech sectors, as well as subject matter experts who can provide insights into broader economic, social, and technological dynamics shaping the industry. Today, we're going to talk about nuclear power. And to be clear, we're talking primarily about fission today, not fusion, that is splitting atoms to produce energy versus combining them. But before we jump to Sukesh, I'm going to set the table for our discussion today. Rather suddenly, and for a number of reasons, nuclear is getting a lot of attention. Load growth driven by reshoring, new large loads like data centers, and of course, the push for economy-wide electrification in many states is driving interest in resources that can provide clean baseload power, particularly to complement variable renewable generation. Many are likely aware that Meta is slowly moving forward with a PPA with Constellation to reactivate one of the reactors at 3 Mile Island in Pennsylvania in a deal that's getting a lot of attention and is intended to meet the increased energy demand triggered by AI. Nuclear generating facilities comprise about 25% of our generating capacity here in ISO New England, and that figure is about 20% nationally. Of course, siting new generation facilities, both fossil and renewable, is difficult, but there are opportunities to increase power generating capacity at existing nuclear facilities known as uprating. And that opportunity exists at many of the existing 54 nuclear facilities around the country. As noted in DOE's Advanced Nuclear Liftoff study in 2022, utilities were shutting down nuclear reactors. In 2024. They were extending nuclear reactor operations to 80 years, planning to uprate capacity and restarting formerly closed reactors. And to accelerate this progress, US DOE and industry are investing in a new generation of so-called advanced nuclear reactors, including SMRs or small modular reactors, which proponents claim are safer and more versatile, including reactors that produce high-grade heat for nearby, tough-to-decarbonize industrial applications. Struggles to build out new clean energy resources have many US climate policymakers thinking twice about nuclear, and with the completion of 2 new advanced nuclear reactors at the Vogtle facility in Georgia, those are the first reactors to go online, I believe, in 30 years in the country, the supply chain and workforce have been revitalized somewhat. That said, the cost of nuclear energy remains high, and while the 3 cent per kilowatt hour IRA investment tax credit is expected to survive, permitting new nuclear even smaller scale is daunting. However, while there remains some resistance to nuclear, that opposition is diminished. Polling indicates that support for expansion of nuclear power in the US has strengthened over the last decade, though that support is a relatively slim majority. It's also worth noting briefly that the only SMRs operating globally right now are in Russia, China, and India, although many more are in development. Here in Massachusetts, I'll note that our colleagues at the Massachusetts Department of Environmental Protection shared with me that DEP has been a leader in acknowledging nuclear power as clean under our Clean Energy Standard policy since 2018. And new nuclear is fully eligible, including if located in New York or Eastern Canada. And Seabrook and Millstone, the generating facilities in New Hampshire and Connecticut, are both acknowledged by the state as clean energy sources. So hopefully that helps set the table. Before we pivot to Sukesh, just a bit of housekeeping for those listening in. As usual, please feel free to drop questions in the Q&A. And we'll reserve some time near the end of our dialogue with Sukesh and do our best to address those. So once again, Sukesh, welcome. You have been a professor of nuclear engineering at the University of Massachusetts Lowell. You serve as Associate Dean for Research and Graduate Studies in the Francis College of Engineering. How long have you been at UMass Lowell, Sukesh?
Well, Galen and MassCEC, thank you for having me and having this dialogue around energy and how important it is. You know, it has always been important for us, and so thank you again for having the opportunity to get into the dialogue. So to answer your question, I came to UMass Lowell in 2012, and that was after about 15 years of an academic career in the state of Texas.
Mm.
And I was like what you mentioned with the Vogel, which was the 2 units that were built recently, were the first new units built in 30 years. I was also the first new nuclear engineering professor hired at the only state university with an ABET accredited nuclear engineering program in New England after 28 years. So we've had a nuclear engineering program at UMass Lowell since the 1960s and 70s and has continued, but they've not hired any new people. So that was a sign in terms of the commitment to maintain that nuclear program and then the revitalization. So
That's great. Thanks for that history. That is indeed symbolic. First hire in that practice in many years. So why don't we just start with some basics? I know I tried to do a little bit of that with the table setting, but can you just talk about first legacy nuclear generating facilities, the so-called large water reactors, and the technology, the scale of those reactors, basically our existing fleet, just at a high level, and how that differs from in terms from advanced nuclear in terms of technology and scale.
So, I mean, the short statement that you provided there, it was compacted with so much, just like the nuclear energy, which is a high compacted, high density energy density, right? So there's so many things that are really exciting about what's going on right now, and also for what we've done as a country and as you know, in our impact as nuclear energy globally in the past 60 years. So nuclear energy is sort of you know, a relatively maturing technology of energy in compared to other energy technologies. I mean, wind energy as we use it today and build is also a relatively young, but we've done windmills for decades. I mean, for centuries, right? Whereas nuclear technology was literally understood in terms of science in the 1930s, and then we designed engineering systems in the 40s and started building them in the 60s and 70s. So approximately 437 reactors currently operate in the world, of which 93 of them are in the United States. So we still have about 0.25% of all operating nuclear reactors in the world, and hence by far the largest fleet of nuclear reactors in the world. Which you already mentioned, about 20%, so 1 in 5 days of your electrical power in the United States comes from a nuclear power station. These reactors were all basically designed back in the 60s and 70s with what is shorthand to light water reactors. So light water reactor is the coolant that is used inside the reactor is the regular water that you and I drink. It's just basically deionized, and that's about it. The only difference. So, or if you wear one of those, sleep apnea machines, you also put deionized water in there. So it's about the same. So nothing fancy about that water. And the simplicity of the design is that not only do you use the light water, which is abundantly available as a coolant, but it is also used as a moderator. And so I'm introducing some of the fundamental terminologies, which will be important for us to maybe explore as we go into the advanced reactors and what does that mean. So, because we know how to use water as a thermal cycle, which we've done in other, energy systems, it was a convenient use of light water for moderation, which means we slow down the neutrons from where they're born to how do we cause fission. And then it also is what we use for cooling, which is essentially take that about 360 degrees of C of temperature, and then remove that and convert that into mechanical energy instead of turbines, and then eventually convert that into electricity. So that was the majority of all of the built that were there, and that is the legacy reactors. The average design size of these reactors, started out earlier in the 500 to 600 megawatt electric. The ones, the Vogtle plants that you just talked about are called the AP1000, designed by Westinghouse, are about
Mm.
1,000 megawatt of electrics. So that's where the delineation on line is. So we call these gigawatt reactors. So these are essentially all of the ones that we have currently in the US that connect to the grid for mainly baseload power supply.
Mm. And the Westinghouse reactors are built in the U.S.?
So the Westinghouse design, originally actually the pressurized water reactor design, and so within the light water category of all the reactors that we run, there's
Mm.
two different categories. One which is the boiling water reactor. It's basically the most simplest of energy design systems. It's like boiling water, for pasta, right?
Mm.
And then there's and I don't want to get into the too much of I don't want to discount the fact that there are some experts in the audience, but I don't want to get into the weeds. But so when you increase the pressure, you can basically also increase the temperature at which the water will boil. So the
Mm.
pressurized water, we increase the pressure from atmospheric pressure to about 1,000 to 1,200 psi, and that allows us to increase the operating temperature. And what you gain by that is thermal efficiency. So you can
Mm.
essentially get a little more higher energy steam that gives you a little more power. But
Makes
a
sense.
little bit of the capital cost. So there's, both designs have validity in terms of economics. Both designs are, technologically sound. It just depends on where you optimize.
Great. And so that the difference then between the legacy reactors and the was it the AP1000s, I believe, in at Vogtle, what are two or three of the kind of key attributes that differentiate this new generation of reactors from the legacy reactors?
So again, a fantastic question for us to sort of re-engage in the conversations or continue to increase the awareness around what's going on with the nuclear reactors, right? Because I think oftentimes, depending on how far or close you are to the technology, you think nuclear, you may consider fission and fusion to be the same. Thank you for differentiating that. Likewise, when you think nuclear fission reactors, the Model F Ford, if you ask somebody to describe the attributes of that design, it actually has an internal combustion engine and it has four tires and a gear, right? But then if you ask somebody to describe a modern hybrid reactor, a car, in a most fundamental way, it also has an internal combustion engine and four tires and brakes and gears, but they're completely different and not comparable in terms of what it is, right? So where are the changes, right? So when we started to design the first generation reactors, and we build majority of the reactors that we build are the generation 2 reactors. These are the reactors that are currently operating in the United States. None of them are in the state in which they were originally designed, because with our own operational history of learning things, engineering, as most of you who own a car or a home or any other system that is designed, you make improvements to them as you learn when you're operating them. So they continue to evolve, adding additional safety features. I think you referenced this idea of uprating. So essentially, as you try to squeeze out more energy from them, so majority of these reactors have gone through that improvement in efficiency of recovering more energy and through the thermal
Mhm.
cycle. For every accident, whether it has the sort of the legacy, like the Chernobyls, the 3 Mile Islands, and the Fukushimas, but any minor incidences also leads to the awareness of where we need to improve things. So those improvements are continuing required by the NRC, the Nuclear Regulatory Commission. These reactors have to demonstrate that they continue to operate under the safety conditions, and the NRC, has those license auditors that continue to review the audits, the safety operation. We want to call them not the legacy reactors, but the generation 3+ reactors. But
Mm.
as you get into the generation 3 and 3+ reactors, which is majority of all the most reactors built outside of the OECD countries, right? So as you start to build new reactors in the 1990s and 2000s, so a lot of them, all reactors built in China, for instance,
Mm.
a lot of the reactors, the new builds in Japan, South Korea, and other countries, they essentially took a lot of the lessons learned. And, for instance, you may have some kind of a harness that will protect you from going into an impact accident in a car. So that's, basically a Volvo made that, and that's their symbol, the car seat, right? But if you buy any new modern car, it automatically has it in there, right? So similarly, Mercedes does this sort of the automatic braking systems to avoid collision. Now, most majority of the modern cars have that as a required feature.
So
So
the passive cooling, for example, at Vogel will likely become, or perhaps become, a feature.
yeah, so I would sort of, this is a great place to sort of introduce the fundamental concepts that were the drivers for what was, lessons learned broadly as a reactor design concepts. And those were lumped under the Generation 4 reactor designs. So passive safety is something that you mentioned. So, how do you so there are four major attributes to this, improvements in design, right? Sustainability, which means you improve your efficiency of utilization of fuel. Economics, make it efficient to run in an economic scale, right? Safety and reliability, right? How do you reliably operate the reactors and how do you do them safely? And then also the overall proliferation resistance, right? So these are the four major categories that were the drivers for generation 4 reactors. But the generation 3 plus reactors take some of these things that we've learned. So for instance, passive safety is one of the key features of the AP1000.
Mm.
Operability and less number of alarms. So if you look at the accident report from 3 Mile Island, there were way too many alarms in the control room, right? So it's overwhelming. I mean, everything is trying, what do I do, right? You simplify that to saying, okay, what is safety critical, what is critical, and what is, I need good to know. It could lead into a further accident
Mm.
analysis, but don't want to have to pay attention to all of them. So that's the kind of things that we've been doing to improve the operability of these reactors by design and making them safer.
Great. Thank you. It's a little bit in the weeds, but I think this is interesting because we're very interested in better leveraging waste heat in the Commonwealth as part of a much broader effort to improve efficiency, potentially look at district energy systems, recapture heat in buildings, and so on from industrial processes. So that was also another feature that kind of leapt out at me with regard to these advanced reactors, is that there might be more or greater opportunities to harvest higher grade heat for nearby industrial processes. Is there a reason why that wasn't done in the past, or is there something about these new designs that enables that functionality?
Again, I think it's a really great question to sort of peel the onion a little bit more, right? So when we design the light water reactors, the generation 3, and then the improvements to the inherent safety features, which is the passive safety systems that we just alluded to, and the operability and the reduced, sort of the radiation release factors through improvements in fuel design and other things. But the fundamental aspect of the design did not change. And so I'll again use the car example from going from internal combustion engine, we went to a hybrid engine, right? So you're still using internal combustion engine, but you're improving the fuel efficiency. But fundamentally, the EVs, the electrical vehicles, are completely different, right? They're fundamentally different now. The engine is completely different. So how do I relate that to nuclear technology? So all of the generation 3 plus reactors are still light water reactor based technologies. But we know that if we really wanted to sort of amplify our ability to truly, hit on that fuel efficiency, right? The way that we totally sort of be accountable on the total energy utilization. If we wanted to minimize the spent fuel that comes off the reactor, right? How do I reduce that, right? And I want to be more economically competitive, right? And I want to be more versatile, right? So these designs that we've just built in the past, they all did one thing, and that was baseload power as a
Mhm.
replacement to coal power stations, right? So they produce steam, and then that steam converted into electricity. But that's not the only thing that nuclear can do, right? So if you take the nuclear energy in itself and then now start to think about, hey, what else can I do, right? So I can provide you with steam if you need it instead of producing electrons, right? And now you do away with this tremendous inefficiency in the thermal cycle, right? So there's no way I can beat the Rankine cycle. It has nothing to do with nuclear.
Okay.
I'm stuck with the 40% efficiency. But if
The
I
same thing that brought us CHP, right? Back in, yes, the reason why that makes sense. Combined heat and power. Sorry, should
yeah,
use fewer acronyms.
We can geek out a little bit. I'm sure the audience there is ready to go. So now, let's say we want to produce steam, right? Now I can provide that using a nuclear system, right? I know I can do it. I just have to change the design, right? So there are several of these advanced reactors that are specifically designed to provide you with process heat. Now, some of them may not want steam; they just want heat in some kind of a chiller system. Dow Chemicals is one of them that is looking at this. So which means that you may actually now get away from light water reactor coolant and moderated system to a gas cooled system. And I don't want to go into a monologue, but I wanted to kind of start to think about what does advanced reactors mean, right? So advanced reactors fundamentally are now going to step away from being stuck with light water and being stuck with producing electricity to sort of opening up and fanning out all that nuclear can offer, right? So I'm like, all right, do you want steam? Do you want direct district heating capabilities, where I'm going to provide you with heat at a certain amount of temperature in form that you want, whether it's hot water, steam, or whatever. Are you interested in not base load but load following systems, right? I'm a proponent of renewable energy. I mean, I have solar panels on my roof. I have solar batteries in my garage, because I think that it is a fantastic way to take advantage of the energy that is available to us in a meaningful way. But as you start to build that renewable into the grid, you need to have the grid to be more responsive and dynamic, right? And so the new energy systems that are designed for grid connection need to be responsive, and nuclear can play an important role there. In fact, in the past, it was considered that renewable and nuclear are at odds with each other. Honestly, with the advanced reactor technology builds and the designs, we are, in fact, the perfect tango partners, right? We can tango together and we can actually dance the floor, because renewable is fantastic when the wind is blowing and the sun is shining. And nuclear can be a great backbone when it is in a responsive mode, when it is built so that it actually can modulate up and down in the energy demand, right? So there's some really exciting things there. And I want to avoid being monologual, but I think the advanced reactors really are opening that opportunity for nuclear to play in a broader sense with district heating, industrial heating. And that's where some of the major carbon loads are, right? So once you start moving away from electricity, which is a significant transportation sector, industry, those are your other major carbon sources. And for us to truly decarbonize, we got to start thinking about those.
Well, and of course, it would also improve when you can find those applications. It would also improve the project economics for developers if they've got additional offtake agreements with regard to high temp water, steam. So that actually might be a good pivot to the economics. I mean, I think that is one thing that perhaps all Americans have heard over and over again, that nuclear, yes, it's this wonderful clean base load power. I think we should talk about responsible waste disposal in a bit, but leaving that aside for the moment, the economics have been challenging. So um, I'm wondering if you could talk about kind of energy market dynamics and design. There are some nuclear advocates contend that existing wholesale energy markets fail to adequately value nuclear's reliability. Yeah, I was wondering if you could just talk about kind of the project economics and what might need to change with regard to energy markets to facilitate the growth in the space.
Yeah. So, especially in New England and also in any deregulated markets, any energy that is put on the grid, electricity generation on the grid, has to be market competitive. And if you think about renewable energy and nuclear, again, there is this partnership, right? Both renewable energy and nuclear are infrastructure, right? When we're deploying a massive scale of renewable energy, we really have to sort of build out that transmission lines, right? So renewable energy deployment at scale is going to require infrastructure planning, because there's not something that you can build overnight, and there is not something that you're building for short-term return, right? So now natural gas, on the other hand, because the majority of the cost involved in a combined gas cycle plant is the fuel. And when fuel became abundantly available in natural gas, the cost went down, and it doesn't take that long to build a combined gas cycle plant. And now in the fuels sheet, you can really tactically make it available to provide you with very good electricity, right? But if
Mm.
you're going to build up renewable or nuclear, you really have to be mindful about how you're going to do this in a meaningful way. So again, nuclear has learned that the past designs were for, baseload power replacing coal. But if you're going to be competitive today, you need to find that economic, way to do this, right? So on the electricity side, for electricity generation, they, one of the two things that actually kills nuclear on the short term is when you build a gigawatt reactor, it takes a long time to build, and it takes a tremendous amount of capital investment. And when you are trying to build something like this in a mature economies like in the OECD countries, your capex is high,
Mm.
your regulation requirements are higher, your time to connect to the grid is longer, right? And so you have this what is called the cost overruns and time delays, right? So let's take the example of Vogtle. When you do anything that is a first of the kind, you're kind of, straddled with things that you discover as you start to do. And those are nothing to do with the design themselves. It could be something that has to do with the building codes. It could be something that has to do with some new regulatory requirements on environmental impact or ASTM standard, for example, right?
Mm.
So those are the kinds of things that, the generation 3+ reactors and the legacy reactors, these were built to custom at site, right? So now, how do you address this problem? Because you have a huge capital investment because you're building this 1 gigawatt of power on grid, and it takes you 8 years, and you have all these significant delays. So industry learned from it. They said, well, if you do a nth of the kind, you definitely get the economics of scale and the learned workforce that builds it and the learned regulators that know what they're licensing, right? We do this in the construction all the time, right? When you have a large development that comes in, you're able to build, 7 different designs that get built very quickly. But when you want to do a custom home on the
Mm.
coastline of New England, well, you got to deal with everything, how does the bedrock look like? So it's going to be very expensive to build, and you're going to build one of the kind, right? So you have to hire all the guys who may not get a second job, so they want to build in their costs on the first one. But when you have a large development coming up with building 150 of these homes in 6 standardized designs, you can do things, right? So that's one thing that is the modular part comes in, right? So when you modularize things, and this is more of a construction technology development, more so than nuclear, but nuclear is embracing that.
Mm.
That, hey, everything that I can do that doesn't have to be done at site, I can do things that are in the factory or in modular fashion. I can get there quickly. And we see this in bridge building, right? Bridges were built
Sure.
in earlier days. Now you bring sections and then you get them done. So
And
it's
you're building them in a controlled environment as well, not
exactly.
subject to weather, not subject to other outside.
Exactly. Now you can actually take your Six Sigma technology implementation that we do in other places and impose quality assurance and quality control, right? So QA/QC becomes a factor, which is very difficult to do at site on custom build. So that is going to drive cost competitiveness. And just to kind of close the loop on this, on the first of the kind to the nth of the kind, just at Vogtle, same site, 2 units, the time to build and the cost of construction was reduced by 40% on the second unit as compared to the first.
Mm.
There is no substitute for actual experience of the workers that build the plants, actual experience of the engineers that are site managers and project managers. You cannot replace actual experience with books, right? And that's very evident in that build at Vogtle. So I think that in itself is one example where we become cost competitive. The other one is as you start to really penetrate into the modularization and then you shrink the size, right? So let's talk about small modular reactors. So
Mm.
small, by definition, is something that is about 300 megawatts of electric power and less, right? So when you reduce the size, your capital cost is reduced, your ability to build something is faster, and the ability for affordability, right, among customers is wider, right? When you're trying to get a 1,000 megawatt electric plant, your customers are limited, right? It's their utilities. Whereas when you're looking at a 300 megawatt electric, now you become a viable, you have a whole viable customer base of um, industry, right? And so there are two specific examples I want to call out right now that are currently funded under the U.S. Department of Energy's Advanced Reactor Demonstration Project. And this program specifically was put up. We don't want to keep designing another reactor, right? We want to build something because building is believing. And so there are two of these projects that are specifically AMR, so advanced modular reactors, with very specific partners, right? So one is the company is X Energy, that is actually building their first of the kind in Seadrift, Texas, in partnership with Dow Chemicals, right? And the intention there is for them to use process heat, right? So now you're demonstrating the
Right.
versatility of the nuclear energy beyond electricity generation, right? And then the second one that is actually in the mix is the natrium reactor. This was backed, by, so the company is TerraPower. And it made big splash because Bill Gates is the initial investor in TerraPower. And so the natrium reactor is the other one that is actually building in Wyoming for a data center. And I don't know if you kind of alluded to that in the beginning of the conversation, but now we have a whole range of client base that has a demand in a very different way. And I think there are now reactor designs that support that demand, right? So I think that's the exciting part of this AMRs, the advanced modular reactors, and the ability to modularize them and build them in factory so that we can reduce the cost and time to build.
So just in terms of scale, the two projects you just mentioned, are those kind of, as you noted, are those low hundreds of megawatts as far as capacity goes?
Yep. So
Yeah.
the X Energy essentially has a design. It's called the XC100, which is basically they build these modules or packs of 80 megawatts each, so you can sort of build as you go.
Mhm.
So that's the other thing, right? I didn't do. I'm a nuclear engineer by training. I did not understand economics and finance, and I had to learn it to understand it, right? So, which is important because now that design that drives your design decisions, right? If I'm going to build a 300, and so X Energy has this design concept that can give you a package at the end of 320 megawatts of electricity at site, right?
Mhm.
But they do them in increments of 80 megawatts of electricity. Why that is important? Well, that is important for multiple reasons. One, as soon as I get building that 80 megawatt electric, I put it to use, right? So
Mhm.
that's a big challenge, right? When you're building something, you're not generating revenue, and it is basically a cost burden on your balance sheet until the day you start to put it to use, right? So it's like buying a car that you're not using for 5 years. I mean, that's just basically payments going out every day without it being useful to you. So that's a very fundamental way in which these designers have sort of approached this, right? So let's do this in increments so that I can start to provide value proposition right away. The other thing it also does is it reduces the source term, right? So source term is one of the drivers that talk about the EPZ, the evacuation zone. Maybe we'll talk a little bit about safety later on, but that is a important attribution here, right? Because an accident at Fukushima is an accident at 1,000 megawatt of electric power. An accident, even if let's say you have there is no core meltdown. I mean, there's a fundamental difference in the safety and the design, but let's just say even if I was building a light water reactor, if I had an 80 megawatt light water reactor let's say it's an exact design of the Fukushima, right? I only now am contained, and each one has its own unique containment, right? So that it just completely just changes the way in which you're going to respond to that accident, right?
Mhm.
It kind of changes the way your response times go. It changes the way your radiological source term gets defined and everything else in between. But then I mean, I don't know. So I don't want again. Don't want to go to a monologue because I want to have said this as a dialogue. So I hope I kind of answered your question with the X Energy. Um, the TerraPower's natrium reactor, it uses a different kind of fuel. So maybe I'll throw out a couple of these terms. The X Energy uses a fuel type called trisofuel. These looks like little buckyballs.
Mhm.
The A natrium reactor uses metallic fuel. So clearly, when you use metallic fuel, you have different thermal conductivity and some benefits there in fabrication of the fuel itself. And they use both have what is called HALEU fuel. So this is high SA, low enriched uranium fuel. So it's very important to understand why high SA is there, right? And that speaks to that sustainability part. Nuclear fuel, the one that we use today, is capable of producing much more energy than what we extract from it, right? But the reason we have to pull it out every 18 months, or one third of it every 18 months, is because the design specs and the expectations of how much juice we can keep getting out of that fuel design, right?
Mm.
That is a limitation based on the design of the reactor, right? So it's not just the fuel design, but the reactor design drives the fuel design. So these fuels are designed in a reactor with the expectation that you're going to do high SA, which means you're going to run this fuel for a very long time. So that gives you two things. One, you get more juice out of the same apple, right? So more
Mm-hmm.
cider out of the same apple, which means that you're going to have less waste coming out of on the other end. And number two, your operations are going to reduce. So, the only time when a nuclear reactor is not producing energy for the legacy reactors that are there is when they're in the fuel outage, right? When they're replacing the fuel.
Mm-hmm.
So if I now have to go from an 18-month cycle to a 24-month cycle, it actually translates into almost a 20% increase in your revenue generation, right?
Mm.
So imagine some of these designs that actually can do either real-time fueling, which means that they don't have to shut down, or they have fuel cycles that are 6-8 years in requirements, right? So
Mm.
again, makes them very economically competitive and sustainability, right? That you're trying to get more out of it with the same amount of material.
Mm. Actually, you're reminding me of of course, there's the shutdowns necessary for refueling, but if memory serves, there have been times, and I'm sure this has happened at other facilities, where not many, I believe, but times when the now shuttered Pilgrim facility had to be shut down because the receiving waters were too warm. So, somewhat ironically, trying to fight climate change with a clean energy source, but if the ocean waters were too warm to receive the waters coming off the reactor, then the plant had to be either turned down or shut off entirely. And I believe that that's happened a few times over the last couple decades. This might be a good pivot then to the waste side, which of course is a safety consideration, but it's come up a couple times now. I think this is certainly, without any personal judgment, I think this is kind of one of the more popular knocks on nuclear, right? Great, clean power, but what do you do with the waste? How do we handle it responsibly? No one wants it. So you were just getting, I think, at a piece of this, one of the advantages of advanced nuclear, which is that it sounds as though the waste is slightly less problematic. But I'll stop there, or I'll get into trouble. And I'd love to just turn it over to you, Sukesh, and hear your thoughts on safety, including waste issues as they relate to advanced nuclear.
Yeah, so I think those we could tackle both of those are some of the important things that nuclear needs to do in addition to being economically viable and more versatile in its application, right? So first of all, nuclear fuel, unlike anything else, really we hate calling it waste because honestly, it's a resource depending on what your design is, right? So the spent fuel that we have of the past operations of reactors is in a way a resource for potential future designs that we could use, right? Now, that's a national call, right? So India has a 4-phase nuclear fuel cycle where they essentially integrate the utilization of fuel that comes out of one type of reactors into the second type of reactor, right? And that was their strategic decision that they made. We likewise have the understanding of these, light water reactors, epithermal reactors, and fast burner reactors. And we understand the science, we understand the engineering, but because of the decisions that we made, we have what is called a once through cycle, which means that we really sort of use it one time and then we store in place. So we at least in the nuclear world, we don't call it waste because honestly, it's a resource that could be in the right context could be used. The second thing is, I think as US has always been, and we pride ourselves in pushing for higher excellence, demand more than what we can deliver and push that and right. And so I think it is important for us to say, not just for nuclear, but I think we as responsible citizens should ask for any form of human utilization of technology, that we do that responsibly, right? And so sustainability cycles are an important thing in everything that we do, right? Everything from the Coke can that we drink water, soda out of, to using water bottles and plastics, to any form of energy that we put out onto the grid, and any form of energy that we utilize. And New England has done a fantastic job in terms of improving efficiencies in our homes, and how we can do, and that's a sustainability aspect of that same thing, right? If overall, I think we've reduced 25 to 27% of the total energy consumed on the New England grid in the last 10 to 15 years. That in itself is reducing waste, right? Because the less energy that you need, better that you're using it better. So how do we do that in context of nuclear energy? So, I sort of talked about how when you do this high SA, low enriched uranium fuel, you're able to get more juice out of the same apple, in a way, right? But you have to do it by changing the design of the reactor that then drives the design of the fuel, and that allows you to do that. And I talked about these two different types of fuel, the metallic fuel but there is other versions of this reactors that are using different kinds of fuel. And we haven't really talked about sort of that second quantum leap, or so these reactors still sort of use fuel in its solid state, right? So the fuel that goes in the current reactor actually does not change physical form. It stays in the way that it went in, comes out exactly the same way, right? Everything that changes in the reactor fuel is the isotopics in the fuel, right? Which is kind of unique to nuclear, right? No other burning fuel that we use, fossil fuels specifically, ever retain the physical form in which they went in, which means now you have a lower or a bigger challenge in terms of building in sustainability, and which is why we need to replace fossil fuel, right? Because you take something that is in a bound state, and then you burn it, and now it's in an unbound state, and then some of it goes into the atmosphere, and you don't have a way to sort of capture it all. In nuclear, that is one reason. Another reason why we don't call it waste, because the fuel stays exactly the way it is, So in the 18 months of burn cycle, it literally stays in bound inside my fuel rods, right? So I am fully responsible for that fuel. There is nothing that I put outside that was as a result of me using that fuel. But now if I wanted to kind of do something even more cool, right, and really sort of push the boundaries of full utilization, right, what can I do? So that's where you get into going into some of the more fascinating coolant systems, right? So if you now take water, liquids to gas, you can, kind of get some efficiencies there. So there's these high temperature gas cooled reactors. So X Energy is a design that uses that concept. But the other way that you can do it is salt, right? So if you've ever boiled pasta, it is advisable to put some salt in the beginning of the water.
Lower the boiling temperature.
Lower the boiling temperature. Wow, hallelujah. So what did you just do? You just basically took that water and you made it into molten salt, right? So what is molten salt? Molten salt is now really sort of a salt, which will essentially be in its solid state unless it hits a certain amount of temperature. Once it hits that temperature, it now is going to get into a molten state, like the lava, right? And now it's going to get, so that is another very fundamental safety feature, right? So the reactor will essentially not function unless you hit certain temperature conditions. Once you hit those temperature conditions, you are in a molten state, and that's when you're going to get into that sustained fission, right? So as soon as you lose offsite power, or you lose any of your operating conditions, you lose the heat, and the thing that makes your reactor go essentially becomes now solid, and you do not have that functionality. Which is
That's
the exact
fascinating.
opposite of what you have to do now. In an accident scenario, what you need is an offsite power, right? Because you need to keep cooling that fuel. And then you need the backup diesel generators, right? And then with the AP1000s, you have these passive cooling systems where you don't need an operating pump that is pumping the fuel in. You have basically ways in which you drive that passively. So like the convective cooling systems, right? But here, now you're completely replacing the coolant, right? And you're really driving up the utilization of fuel. Well, let's get even more excited and go into things that have really pushed the envelope, right? So not only do I want my fuel to be from what happens if I actually take my fuel that is in a solid state and convert it into liquid state? Now I have a molten fuel and coolant in a bath, right? And so there are these designs that are at least probably about 15, 20 years away, but are being, they're in some experimental states everywhere, where now you're really taking advantage of getting more and more juice out of that apple, right? So you're going away from making what is called a cider to going into making smoothie, right? So what's the difference, right? You smoothie, there is no pulp that comes out, right? You drink all of it. Whereas if the best juicer will still have some pulp at the end, right? And then if you're a responsible and if you have a responsible governance system, you put that pulp to good use, right? And you don't throw it into a landfill site. It's biodegradable. You do something good with it. So those are the kinds of things that are really sort of going into that inherent safety by design, because you have the choices of what you're going to do with your coolant system, the choices with your fuel, choices with your moderator, and that sort of changes the conversation as we get further away from the light water cooled solid state, non-flow fuel types to something that is more advanced in true cases, going past what we can do now.
Got it. Thanks, Sukesh. I know we're just looking at the clock, and I want to make sure that we get to some of the participant questions. But I did want to touch on a couple things, so maybe we can do a little bit more rapid fire. I know that there were, I think, over 9,000 jobs associated with the Vogtle facility in Georgia. So I wonder if you could just quickly touch on workforce. It occurs to me that there are a number of different categories. Of course, there's the construction of the facilities, there's the kind of fuel management, there's ongoing operation and maintenance. Yeah, if you could just talk briefly about kind of the jobs associated with and whether there's transferability. I mean, these are, at the end of the day, um, steam power generating facilities in a sense. So there's some transferability, I assume, from other fossil fuel generating assets.
So there are lots of reasons why Massachusetts needs to lean forward in all forms of clean energy. And then one of those is connected to workforce, right? I mean, Massachusetts is known for many things, and my son actually is on a crew team, and I realized that it's, the rowing is also something that we pride ourselves in as a sport that comes out of Massachusetts. And I recently learned that volleyball apparently is also, comes from Massachusetts. So in Massachusetts, we pride ourselves to be first, right? And we want to be in the business of developing workforce. We are globally known as some of the best academic institutions of higher education. So we want to participate in this infrastructure. We want to provide those jobs to our New England residents in this meaningful way. So Department of Energy actually and the Department of Labor have, their jobs are to kind of look at where the workforce demands are going to be. So they anticipate that there's going to be about 300,000 new jobs in the nuclear field in the whole range of supply chain support and OEMs to the construction management, to the specialized welders, to heavy industries. So as we kind of reshore, there is already a tremendous emphasis on upskilling, right? We're going into advanced manufacturing. We're going into, advanced instrumentation and control systems. We're looking at, high tolerance welding systems. And we want those jobs in New England. We have those jobs in New England. The shipping industry in New Hampshire and in Connecticut and Massachusetts, they are some of the highest paid, trades, right? The trade crafts. So we don't want to miss out on training that workforce for nuclear. And MIT, as a private university, has a nuclear engineering department that does undergraduate, master's, and PhD, and so does UMass Lowell. And there is a range of universities that participate in the fundamental drivers that will lead into, construction engineers, electrical engineers, mechanical engineers, and all of the community colleges and our trade schools, right? All of them are fueling that economics of workforce development. And I think as we start to embrace parts of nuclear power and our contribution to it in the grand scheme of national and international, and hopefully maybe even build some nuclear power stations of the advanced modular reactors or SMRs in New England, we would truly be taking advantage of that workforce, high paid jobs, both in the process of construction, operations, and then also supply chaining it there. So that's what we are looking at, about 300,000 jobs that is going to come out of this demand to maintain the current fleet and to sort of respond to the anticipated conservative scales of what we will be doing in terms of build.
Great. Thanks. Well, maybe we'll just hit on one more and then we'll turn to some of these questions. So it's kind of a way to, I think, close out. And to be clear, there's a lot we haven't addressed. We only had an hour. This is an enormous topic. And I think there's a lot of promise, there's a lot of opportunity. People have a lot of legitimate concerns and questions given the history of nuclear. So a lot needs to be done. But nuclear is increasingly coming up in state level, and to be clear, all states, right? I'm involved with an organization that talks to clean energy leaders across the whole country, and nuclear is quietly coming up more and more. I think because this realization that we just need more options on the table to complement our substantial investments in renewable energy sources. And so, what do you see are some kind of key next steps that leading states need to take in order to begin to address existing challenges, to better understand advanced nuclear technology? Do we just need to kind of begin to talk more about this in public forums and to educate decision makers, opinion leaders about how new nuclear is different than your father's nuclear, as they used to say, or your grandfather's nuclear?
Uh, I think the state of Massachusetts and New England in general always challenged the norm, right? I mean, hey, we were the ones. I mean, that's why, we challenged the colonials by throwing the tea out there, right? So, I mean, we are leaders, right? We are natural leaders, and we are naturally embrace technology. So, I think what I would love to see is a revitalization of honest conversations among citizens. I am not a believer that just because I don't have any other solution, I'm going to have to accept this as a solution, right? And I think there is a strong belief in Massachusetts that, I can do better. Just because I don't have any other choices, I don't have to accept a choice that I'm not convinced that it's the right choice. However, I think we also then have to be honest about saying, I cannot judge and have a formed opinion that I rode in the Model T and it was a fun ride, but it's an antique, and that's what my impression of what a car is.
And it was
Right?
really unsafe.
It was really insane, but it was a state of the art at the time that was built,
Right.
right? So I think we are capable as citizens, and we are capable as policymakers to really, at least, and just because I talk to you does not mean that I am going to agree unless you convince me otherwise. But unless you come with an open mind to actually genuinely talk to me about it, and I mean, if hey, listen, if nuclear guys cannot answer your questions in a scientific way to prove to you that they have genuinely addressed the issues concerned with safety, operations, sustainability, what are you going to do with your spent fuel, how are you going to be market competitive, then you shouldn't. Why would you, right? I mean, I don't hire a guy to cut my lawn just because I don't have a choice, right? But I want to be convinced that the guy is going to deliver, right? And if he delivers, then sure, I eventually give him the entire landscaping job. So I think that this right now is a time, and I think the Governor Healy took a very significant step in that direction, and then the state legislature took a very important step in the climate bill, right? The climate bill prioritizes clean energy. But it now says, well, listen, you can acknowledge that nuclear can provide clean energy. And that was a very significant step, right? Look, I think it was sort of naive for us to ignore the fact that our neighbors in New Hampshire and in Connecticut continue to provide a significant amount of clean energy from nuclear that we benefit from, and we didn't acknowledge that, right? And it then allow our utilities that operated in Massachusetts to participate in those power purchase agreements on those nuclear power stations in the country. So I think that Governor Healy took a very bold step. a necessary step to acknowledge that nuclear is continuing to play an important role in the existing reactors, and I think that we have to accept it. And I think that shows the maturity of our legislature, our executive branch, and I think they represent the public. And I feel that when I moved to Massachusetts from Texas, people said, "What are you doing? This is an anti-nuclear state." And I honestly am running into more and more people who are so informed and are so interested in learning how do we take advantage of these, are these real, right? And they're real. I mean, we're building these things. I don't think Microsoft, Google, Meta, and Amazon and OpenAI are going to step up and open up a 1.6 to $2 billion each if they didn't think that this is a real solution. Look, if one industry that has no commitment to anybody is the IT industry, right? They're the natural disruptors. They question everything that is a status quo, and they have a very short attention span, right? If they don't see a solution, they move on, right? And when they are stuck with nuclear, that is another way in looking at this as a reinforcement of how I think it's a validation that these guys are now saying, listen, nuclear might be ready,
Mhm.
and it took us 50 years to get ready, right? We had to learn how to operate a little bit more responsibly. We had to learn how to regulate a little bit more better. And like all engineering systems, there are some accidents that come along the way. I mean, come on, we have to accept that there was no accident that led outside of Chernobyl, and that's a whole different thing that can be a 2-hour conversation in itself. That we did. So as you can see, I'm passionate. I'm raising kids that I want to leave something behind that's important, but I love being challenged. So I think we should have an honest conversation. We continue to do these kinds of things, and let's just be open to listening to the other side.
That's great. That's wonderful, Sukesh. Thanks for that. Agree. We need more hard conversations, particularly now. And we need to be reminded about keeping our eyes on the prize, which is the bigger fight against climate change and all of the negative impacts that is already bringing and will continue to bring. But there's one question about, and you raised this a bit, and we're certainly looking at it as we think about data centers, but load flexibility and how these smaller reactors are potentially better at following loads. Is the industry thinking about combining storage with nuclear? Is that a good fit, or is that somewhat redundant? Is it helpful? Is it?
I mean, and we've not rehearsed this at all, so I didn't know what you were going to be asking. But I think these are the kinds of questions, and I mean, I'm actually very encouraged. There's 27 open questions on there, and I think I'm just browsing through, and we've been addressing some of these. So there are about 6 to 7, and if you consider some of the advanced 3+ reactors like GE Hitachi, NuScale, there's probably about 10 to 12 different designs that really solve many of these different problems. And many of them specifically, and TerraPower actually has the built-in energy storage system in form of thermal storage, right? And when you go into molten salts, that's another way in which you can take advantage of that. So yes, there is a built-in storage system. And a lot of them actually are conducive to what is cogen, right? So now you can envision a sort of an energy island where you may have renewable energy sources, a 150 to 200 megawatt nuclear system, a thermal energy storage system, and possibly a hydrogen generation system, right? So now you're really sort of taking advantage of all these different energy needs in one location in a scaled form. The one
Thanks.
thing
Yeah.
we did not talk about, and I don't want to remiss the opportunity, is just if we do not get to the table, and just because we know everything we do, and if we are willing to ask the hard questions on the global scale, we are going to miss the opportunity to drive safe, secure, and a responsible build of nuclear power stations. The Chinese and the Russians are out there building these. Americans can talk about it. We discovered the technology. We built the first kind, and we still operate the largest fleet in the world. But if we do not step up and engage in a conversation, we will not be driving the conversations around how we get these reactors get built. So I think it is also something that we really have to think about.
Yeah, agreed. I mean, that might be a good way to close this out, and that there's certainly an international competitiveness component to this discussion. Well, I'm sorry that we weren't able to get to more of those questions, but I think that this is a good start to, I think, what will hopefully be an ongoing dialogue in this state, in our region. I think it's about time we start talking about it. And as you said, we're gonna have to have a lot of conversations to kind of move the ball forward and address a lot of serious concerns. But there's an opportunity for us to move on this clean energy source and keep pace with our competitors and complement our very ambitious renewable energy and electrify everything objectives. So thanks so much for your time, Sukesh. Really appreciate you and the dialogue. Appreciate everyone joining today, and it's been a great conversation.
Well, I appreciate MassCEC's leadership in keeping clean energy front and center for New England, and I appreciate your leadership in sort of reaching out and starting this conversation. And honestly, there is so much information flowing into the Q&A session, with a lot of people actually sharing some of the things that they know. I am really excited that we did this, and I think that there is maybe a roadshow that we may take. I mean, I want to learn more from others because there's so much there. That there's I mean, nuclear is a system, right? It's not one small part of it. It literally is an entire, I mean, it drove building fire stations, and our emergency response, FEMA, came out of
Mm,
nuclear power station bill, right? We drive, nuclear power stations drive a larger economics, economy and infrastructure. So very, very important that we keep talking about this. So thank you.
great. Wonderful. All right. Thanks all. Thanks for joining today. Thanks again, Sukesh. Take care, all.